Before we talk about slant asymptotes, let me just remind you that slant asymptotes will only occur when the degree of the numerator is 1 greater than the degree of the denominator. So on these two graphs here, you can see that the degree of the numerator, 3 is greater than 2, 2 is greater than 1, is greater than the degree of the denominator, so therefore we would definitely not have any horizontal asymptotes. But on both of these cases, the degree of the numerator is just 1 unit greater than the degree of the denominator. So on both of these graphs would have slant asymptotes. Now let's just take a look at this one for just a second. Let's say this was a 5 instead of a 3 right here. Well, then the degree would not be 1 greater, it would actually be 3 greater than the degree of the denominator. So in that case you would not have a slant asymptote at all. Okay, but anyway, the way you find the slant asymptotes, let me show you how you find the slant asymptotes. So let's just start with this example here. So if I wanted to find the slant asymptote for this second example here, what you do is you do long division, and you actually divide the denominator into the numerator using long division. And then the result will actually be your slant asymptote. Now when I say result, I mean the quotient. The remainder is not relevant, but the quotient is what you use for the slant asymptote. So let me show you an example of that. So here is that same function. I'm going to divide x plus 2 into 3x squared minus 1, the numerator. So I'm going to divide the denominator into the numerator. So the first thing I'd do is I'd say, okay, what times x would give me 3x squared? So obviously that would be 3x. And then you multiply back 3x times x, you get 3x squared. And then 3x times 2 gives you 6x. Well, then you know, in long division, remember, then you subtract. So I have 3x squared minus 3x squared, so the 3x squareds will cancel. I have no x term here, so I would just have 0 minus 6x when I subtract, so I get minus 6x. And then I would bring down the next lowest degree term, which is actually a negative 1, so bring down the negative 1. Okay, so now you say, okay, what do I multiply by x to get negative 6x? Well, that would be negative 6, so your next term would be minus 6. And then when you multiply back, you get negative 6 times x, which is negative 6x, and negative 6 times 2 gives me negative 12. And then, of course, you subtract that. And I'm going to get a remainder, but like I said, the remainder is irrelevant. When you subtract, you're going to get minus 6x plus 6x, so those are going to cancel. And then you'll get minus 1 plus 12, which gives me 11. So therefore, the remainder would be 11 over x plus 2. But again, the remainder is irrelevant. What you want is simply the quotient. So this line, y equals 3x minus 6, is actually your slant asymptote. So if you look over here, here's the graph of this. And then this right here is actually that line, y equal 3x minus 6. And notice that as x gets large, notice how this graph gets closer and closer and closer to that line, but it also does the same thing in the negative sense. As x goes to negative infinity, the graph gets closer and closer to that line, y equals 3x minus 6. So that's how you find a slant asymptote. And I might do another one here for you in a minute, but let me just summarize now on these graphs. Let's finish up this one. So on this graph, you had a vertical asymptote of negative 2, because you know that negative 2 makes the denominator 0. And as I said, you had a slant asymptote of 3x minus 6. Let me draw the vertical asymptote for you real quick. See if I can put it in here without too much difficulty. So let's see, let's put that there, maybe back there. Okay, let's make that dotted or a broken line. Okay, so this right here is the vertical asymptote x equal -2, and you already know that the black broken line is the slant asymptote. And the other thing is, if you wanted to find the intercepts for this graph, if you let x be 0, you would get -1/2, which is -1/2. So you can't really tell here what it is, but that point right there, where you see where the arrow is, that's the, I'm sorry, wait a minute. Okay, that's the y-intercept, not the x-intercept. So when x is 0, y is -1/2. So actually, let's blow it up a little bit. So you can see right here that the graph crosses the y-axis just below the x-axis. So that's the point 0, -1/2. Now, if you want the x-intercepts, you actually would have to set this equal to 0. And so if you set that equal to 0 and solved it, you would get 3x squared minus 1 equals 0. And then you can do this on scratch paper. You get 3x squared equals 1. Then divide both sides by 3. You get x squared equals 1/3. And then if you take the square root, you get x equals plus or minus the square root of 1/3. So if you look here, notice that right here the graph crosses the x-axis, and also right here the graph crosses the x-axis. So that would be those two x-intercepts, plus square root of 1/3, 0, and minus square root of 1/3, 0. Okay? All right. Now, going back to this one, this is one we looked at earlier. We already know the vertical asymptotes are x equal -5 and x equal 5. And we already know the horizontal asymptote is just the x-axis, or the line y equals 0. And we learned earlier that it crosses the y-axis just slightly above the x-axis. So very small number, 0, 3/25, and it crossed the x-axis at the point 3/2, 0. So by finding out this information about asymptotes and the intercepts, most of the time you can get a rough graph of these rational functions. Okay, this is another one that we looked at earlier. So in this one, let's see, we knew that this one had a horizontal asymptote of y equal 2/3, and so there's the horizontal asymptote y equal 2/3. And then we know that when x was 0, it crossed the y-axis at -1/2, so that would be right there. And then also, if you wanted to find the x-intercepts, you'd have to do something that I did similar to number 2, set that equal to 0 and solve it, and you would get x equals plus or minus the square root of 1/2. So that would be right here would be minus the square root of 1/2, and right here would be plus the square root of 1/2. So those values are approximately -0.7 and positive 0.7. If you plug that in the calculator, you can see that. I'll end this video. I'll show you one more example of finding the slant asymptote. You'll have to forgive my structure here. I tried to do it on the computer. But let's take a look at this function right here. Now, since the degree of this is 1 greater than the degree of this, then we know we're going to have a slant asymptote. So I'm going to divide 3x squared plus 2 into the numerator, 2x cubed minus 1. Now, I had to figure out what can I multiply by 3 to get 2, and it turns out I need 2/3. So the quotient would be 2/3, and then what do I multiply by x squared to get x cubed? It would be x. So I'd have to multiply this by 2/3 x. So then when I multiply back, I get 2/3 times this, that's going to be 2x cubed, and then 2/3 times 2 is going to be 4/3. Well, when I subtract this from the top, the 2x cubes cancel, and then since I don't have an x term up here, if I subtract, I get minus 4/3 x minus 1. Now, this is actually, the degree of this is actually less than the degree of 3x squared. So I'm actually done, because I don't care about the remainder. All I care about is just the quotient portion. So the slant asymptote would actually be that quotient 2/3 x. So y equal 2/3 x would be the slant asymptote for this function. And to wrap it up, let me just show that to you. So here's the graph of that function, and that broken blue line there is the graph y equal 2/3 x. And so notice that as x increases, it gets closer and closer to this slanted line. And also as x decreases, notice that the graph gets closer and closer to that slanted line. Okay, so this ends the discussion that I have on rational functions. So I believe the only thing left for us to do now is to talk about exponential and log functions in order to finish this module.